Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in last lecture we have completed unit number 3, that is singularity. So with this lecture, in this lecture we will start unit number 4, that is residue. Okay, so in this lecture we will see the definition of the residue and some examples on a residue. Then we will see one theorem on a residue. Okay, so first we will see definition of the residue. What do you mean by residue? Okay, so to define a residue, let us suppose that f of z be a analytic function with a singularity at z equal to a. Then f of z can be expressed as f of z equal to summation n equal to minus infinity to infinity a n z minus a to the power n. Okay, which is called as the Laurent series. Okay, so where a n is f n of a upon n factorial, which is given as 1 upon 2 pi integral over gamma f of z upon z minus a to the power n plus 1 dz. Okay, so this is the definition of the residue. Residue means which is f of z is analytic function with a singularity at z equal to a. Then f of z can be expressed as a Laurent series and which is given in this type. Okay. Now we will see there's another definition, that is residue of the function f is defined as coefficient of 1 upon z minus a in the Laurent series expansion, and it is denoted by residue of f at a point a equal to a minus 1. Okay, but a minus 1 equal to 1 upon 2 pi integral over gamma f of z upon z minus a to the power minus 1 plus 1 dz, and this is nothing but that is 1 upon 2 pi integral over gamma f of z dz. Okay, so therefore residue of f at a point a equal to a minus equal to 1 upon 2 pi integral over curve gamma f of z into dz. So this is the definition of the residue. Okay, now we will see some examples on a residue. Find out the residue of the following function at z equal to 0. So this is the first example, sin z upon z to the power 4. Second example, e to the power 2 by 3, and third example is sin z upon z. Okay, so these are the given function. Now we will find out the residue of these three functions. Okay, so for first function, first we will solve the first. So here we have given sin z. Let us suppose that f of z equal to sin z, and we know that the sin z series. So sin z series can be written as z minus z cube upon 3 factorial plus z to the power 5 upon 5 factorial minus z to the power 7 upon 7 factorial plus and so on. So this is the sin z series. Okay. Now we will divide. Now dividing on both sides by z to the power 4. We want this term. Okay, f of z. So dividing on both sides sin z upon z to the power 4. Okay. So 1 upon z to the power 3 minus 1 upon 3 factorial 1 upon z plus z upon 5 factorial minus z to the power 3 upon 7 factorial plus and so on. Okay. Now by using the definition of the residue at a point a is that is 0. At a point z equal to a means 0. Okay. So therefore it is defined as a residue of f of z, and f of z means that is sin z upon z to the power 4, and at a point a means 0, a is 0, which is equal to coefficient of 1 upon z minus a in f of z, that is coefficient of 1 upon z, coefficient of 1 upon z, that is minus 1 upon z, minus 1 upon z. Okay, so put the values of 1 upon z, 1 upon coefficient of 1 upon z, that is minus 1 upon 3 factorial, coefficient of 1 upon z, that is 1 upon 3 factorial. So which is equal to minus 1 upon 6. Now we will see second example. The given as e to the power 2 upon 3. Okay. So we know that e to the power z at a point z equal to 0. That is 1 plus z plus z square upon 2 factorial plus z cube upon 3 factorial plus and so on. Okay. So now we will put e to the power 2 upon z. Instead of z we will put 2 upon z. So therefore 1 upon 2 by z plus 2 by z bracket square upon 2 factorial plus 2 by z bracket cube upon 3 factorial plus and so on. Okay. So which implies 1 upon 1 plus 2 upon z plus 2 upon z square plus 8 upon z cube 3 factorial plus and so on. Okay. So in this way we can write 1 plus z upon 2 plus 2 upon z square plus 4 upon z cube divided into 3 factorial into 3 that is 4 by 3, that is 4 by 3. Okay. Now by using the definition of the residue, and which is defined as residue of f at a point A, and which is given as coefficient of 1 upon z minus a in f of z. So this is the value of f of z. This is the value of f of z, that is 2 upon z, 2 upon z. So this is the value of f of z. Okay. So what is the coefficient of f of z? That is 1 upon 2. 1 upon z minus c, that is 1 upon 2, that is z minus 0, that is 1 upon z, that is this is 2. So therefore residue of f of z, is that is e to the power 2 upon z at a point a is 0. Okay. So 1 upon z minus a, that is 1 upon z minus a is 0. So therefore coefficient of 1 upon z minus that is 2. So therefore residue of e to the power z 2 by z at point 0 is 2. So similarly, we can find out the residue of sin z upon z. Okay. So residue of sin z upon z at a point 0, we will get 0. Okay. So these are the some examples of the residue at a point z equal to 0. Now we will see the theorem. What is this theorem? State and prove Cauchy residue theorem. The statement of the Cauchy residue theorem is given as let f be a analytic in the region G except for a isolated singularity at a1 a2 am, and let gamma be a closed rectifiable curve in a G not passing through the points a1 a2 am. Then we have to prove that 1 upon 2 pi I integral over gamma f of z dz equal to summation k equal to 1 to m. Index of a closed curve at gamma at a point ak into residue of f at a point ak. Okay. So we have to prove this theorem. Okay. So what is the proof? So to prove this theorem, let us define a function f is analytic. Okay, except for a isolated singularity a1 a2 am. Construct a disk. Let us construct a disk where a1 a2 am. Construct a disk a1 a2 am. Sorry, c1 c2 cm be the centers and a1 a2 am be the uh, points, residue, extreme points. Then radii is 1 r1 r2 rm respectively, chosen such that number 1 each of ci lies inside the gamma. Okay, where c1 c2 cn which is lies inside the core gamma. None of ck intersect gamma, that is k equal to 1 to n. c1 c2 cm do not intersect each other, and let us we denote gamma k, that is mod z minus ak equal to gamma k, which represent a circle whose center ak and radius is gamma k rk, where k is 1 to m. Okay. Now let us we define a closed curve D as, and which is defined as D equal to gamma minus gamma 1 minus gamma 2 and so on gamma m. So gamma minus, this can be written as gamma minus gamma 1 plus and so on gamma m. Okay, so here variable z, it travels the curve gamma in the anti-clockwise direction, where gamma 1 gamma 2 gamma m in a clockwise direction as shown in figure. Okay, now okay, that is we can see that closed curve D such that all the isolated singularity are excluded from that. So therefore f is analytic in a closed curve D. So therefore by using Cauchy's theorem, integral over D f of z dz equal to 0. So therefore integral f dz equal to 0 at a curve gamma minus gamma 1 plus gamma 2 plus and so on gamma m. Okay, so this is the curve. Okay, so this can be written as, we will separate the curve integral over curve gamma f dz minus integral over curve gamma 1 f1 f of z and so on equal to 0. Okay, now we will separate the integral. Okay, separate integral and transfer this integral to RHS side. So and multiplying 1 upon 2 pi on both sides. So integral or curve gamma f dz equal to integral curve gamma 1 f dz gamma 2 f dz and so on gamma m f dz. Let us we consider equation number 1. Okay, now consider integral over gamma k f of z dz for any I equal to 1 to m. So we have given f is analytic except singularity a1 to am. It can be represented as f of z equal to summation n equal to 0 minus infinity to plus infinity bn z minus ak to the power n. Okay, so hence we can write integral over gamma k f of z dz equal to integral over gamma k n equal to minus infinity to plus infinity bn z minus ak to the power n dz. Okay, so hence we can write as, so this is a series which is uniformly convergent. So this series is a uniformly convergent. Okay, but gamma I in mod z minus ai equal to gamma I. Okay, so therefore integral over gamma I z minus ai to the power n dz exists for n equal to minus 1 only. So therefore for all other integers values is 0. So therefore we can write as integral over gamma k of z dz equal to b minus integral of gamma k z minus a k to the power minus 1 dz. Okay, so multiplying on both sides 1 upon 2 pi I. So we get 1 upon 2 pi integral over gamma k f of z dz equal to b minus 1 upon 2 pi I integral over gamma k z minus a upon I. Okay, so this is b minus 1 is multiplied. So by using the definition of residue, this can be written as residue of f at a point ak index of closed curve gamma k a, equation number 2. Now multiply on both sides 1 upon 2 pi to equation number 1. Then equation number 1 becomes 1 upon 2 pi integral over gamma f dz equal to 1 upon 2 pi integral gamma 1 gamma 2 and so on up to gamma m. Okay, so therefore by using the residue definition, so this term can be written as a residue of f a1 index of closed curve gamma 1 a1 and f2 a2 gamma 2 a2 and so on up to fm gamma m. Okay, so in this way we can write the by using the definition of the residue. Okay, and this is nothing but we can write in the summation form, summation equal to k to 1 residue of f ak n gamma ak. Okay, so this is the first theorem of the Cauchy residue theorem. So second theorem is statement if z equal to a is a pole of order m of the function f of z, and if f of z z minus a to the power n into f of z small f of z, then we have to prove that a residue of f at a point a equal to 1 upon m minus 1 factorial into g to the power m minus 1 of a. Okay, so this is the second theorem. So to prove this theorem, we have given that f has a pole of order m at point z equal to a. So therefore by using definition, there exists an analytic function f of z such that f of z equal to z, such that f of z equal to z upon z minus a to the power m. Z of z equal to, okay. So z of z equal to z minus a to the power m into f of z. So we know that by definition of the residue of f at point a equal to 1 upon 2 pi integral or gamma f of z into dz. Okay, so by using the definition of the residue, where gamma is in mod z minus equal to gamma. Okay, so put the value of f of z. So 1 upon 2 pi integral over core gamma f of z means z of z upon z minus a to the power m. F of z means z of z upon z minus a to the power m dz. Okay, and we know that z to the power by using Cauchy higher order derivative formula. So this can be written as z to the power m minus 1 upon m minus 1 factorial. So by using the Cauchy higher order derivative formula, we can write this term. Okay, so this is the second theorem. So here we have to note that a residue of f at a point A can be written as 1 upon m minus 1 factorial integral over core gamma d to the power m minus 1 upon dz to the power m minus 1 derivative z of z. Second, if z equal to a is a simple module, that is m equal to d, then residue of f equal to a z dot of a upon 0 factorial, that is z of a. Okay, so which implies limit z tends to a equal to z of z. Okay, so these are the notes of the theorem. So in this way we can state Cauchy residue theorem, and then we will can prove that Cauchy residue theorem. Okay, so in this lecture we have seen some problems on a residue definition, and some uh, theorems on a residue. Okay, so with this lecture we have completed lecture number 1 of this unit number 4.